Welcome to our final video of Topic 6, Human Physiology. In this video, we're looking at hormones, homeostasis, and reproduction. And that is why we've got our rock design at the back there, because we're looking at how we keep everything in balance. So our essential idea is that hormones are used when signals need to be widely distributed. So we've looked at the nervous system and the nerve impulse. Hormones are a bit different. They travel generally via the bloodstream and can be distributed all over to the body wherever they're needed. Our nature of science, we're looking at developments in scientific research, follow improvements in apparatus. Now, we're looking at William Harvey again. You remember he was looking at the blood system. Now, William Harvey was hampered in his observational research into reproduction by a lack of equipment. The microscope was invented 11 years after his death, so his studies that he was doing, he couldn't get any further because the microscope hadn't at that stage been invented. Okay, your understandings for this unit. We are going to be looking at hormones. And these are chemicals that are synthesized in specific glands throughout the body. And you've got a diagram there with a range of different glands in the human body. They regulate metabolic activities and they maintain homeostasis. So they maintain our constant state, which allows enzymes to do their thing at their optimum rate. Everything is coming together now. Now, hormones are often referred to as the chemical messengers in the body. They're transported around by the blood system, generally. There are some exceptions there. And they are broken down by cells once they have been used. So once they've delivered that message as such, therefore secretion from the glands is an ongoing thing. You can see here a list of different glands and the hormones that they secrete. You don't need to know all of these, but it's actually a really interesting list to look at and to look at the function of those hormones. Again, on the right hand side, you've got the human body with those glands listed in case you want to match across. Okay, so we're going straight into it and we're going to look at how our body controls blood sugar levels. So here we've got insulin and glucagon are secreted by beta and alpha cells, or it could be alpha and beta cells, of the pancreas respectively to control blood glucose concentration. What does that mean? Let's have a look. Okay, so we're going to be looking at the pancreas, and we've looked at the pancreas and its structure before when we was looking at its production of those digestive enzymes. We're looking at it a bit differently now. Okay, so the pancreas detects changes in blood glucose levels. Now, blood glucose should generally be maintained around 5 millimoles per litre. Homeostatic mechanisms are activated by pancreatic hormones, insulin and glycogen. Now these are initiated if the level deviates from that 5 millimole per litre. Okay, so our pancreas is composed of this glandular tissue, and there's two glands in this one organ. The islets of Langerhans secrete hormones directly into the bloodstream. So these glands are the islets of Langerhans are part of these glands. So they're composed of two cells, so two glands composed of the two different cell types. Okay, we've got the alpha cells and the beta cells. Let's have a look a bit closer at each of those. Okay, the alpha cells. These synthesize and secrete glucagon. blood sugar falls below a certain point, it stimulates the breakdown of glycogen to glucose in the liver cells. So glycogen stimulates the breakdown of glycogen to glucose in the liver cells. That glycogen is produced in the alpha cells, which are found in the islets of Langerhans. Glucose is then released into the bloodstream, so it's increased the glucose level in the bloodstream. So they're our alpha cells. Now let's have a look at our beta cells. These synthesize and secrete insulin. If the blood sugar rises above a certain point, then it stimulates the uptake of glucose by various body cells, mainly those in the skeleton and the liver. Okay, this stimulates the conversion of glucose to glycogen. So it's the opposite as what was happening with, so insulin does the opposite to glucogen. So therefore, insulin reduces blood glucose concentration, whereas glucogen increased it. Now, one of the things when we're looking at hormones is there's a lot of graphs, and you need to be able to look at different graphs and see what it's showing you. So on this graph, we've got two vertical axes. We've got blood glucose on the left-hand side and insulin levels on the right-hand side, sorry. Along the horizontal axis, we've got time of the day. And what you can see on this graph is the blood glucose levels, the insulin blood levels. You've got starch in food, you've got sucrose, okay? So you can see the levels throughout the day of these different components. Now your job is to be able to look at that graph and read what it's telling you. Okay, so if you're looking at it tells you on there which axis to read. So glucose, you'd read glucose. Insulin, you'd read the right hand insulin. Starch, okay, you read glucose. And sucrose, you're also reading glucose because they are sugars. Okay, so you need to, and throughout this unit we'll see lots and lots of different graphs so that you can learn to read them. Okay, just look at this graph. What story is it telling you? Choose one thing, say blood glucose. And what story does this graph tell you about blood glucose levels throughout the day? Is there patterns with the blood glucose and insulin, for example? Read the graph, see the pattern, tell the story. Okay, next up, controlling body temperature and metabolism. So we're looking at thyroxine now, another hormone. Thyroxine is secreted by the thyroid gland to regulate the metabolic rate and help control body temperature. So before we go any further, let's think about that. What has body temperature and metabolic rate got in common? Well, metabolic reactions are generally exothermic, release energy. And that energy is transferred as heat energy, which increases the body temperature. So these two work very much hand in hand. Too much metabolic action, too much body temperature, enzymes start to denature. So it's all a balance. So thyroxine, secreted from the thyroid gland. Now it's an interesting molecule. It contains 4 atoms of iodine. So it's not a protein hormone. Okay, so you've got protein hormones and you've got chemical hormones. So this is a chemical hormone. If you've got low iodine in your diet, this is obviously going to impact your thyroxine production. Now, thyroxine regulates metabolism. So the target cells for thyroxine are generally all cells because they're all metabolic. However, especially those that are extremely highly metabolic, such as the liver, brain, and muscle cells. So if you've got a high metabolic rate, you've got an increase in thermal energy transfer, as we said earlier. The more metabolic reactions, because they're exothermic, the more thermal energy that's going to be produced. In normal conditions, a drop in temperature triggers thyroxine secretion to stimulate metabolism. So if you get cold, then thyroxine is increased to increase your metabolism. If there's a thyroxine deficiency, we get this condition called hypothyroidism. Okay, so here we have another graph. Now, just so that you know, we've got some different, if you look down the bottom here, because straight away when you're looking at this graph, you're saying, I've got no idea what this is showing. But you've got some abbreviations. So your TSH is thyroid stimulating hormone. Then you've got T3, and this is that hormone. And then your T4 is your thyroxine. That's the one that we're interested in, that we're studying as such. Now, when you see a graph of this type, I'm not really interested so much in what this graph is showing you. Yes, it's showing us our thyroxine, okay, which is the T, which one did we say? T4, okay, so it's the middle bar we're looking at thyroxine. So what can we say? We can say that over the 12-month period, the level of thyroxine dropped, the level of thyroid stimulating hormone increased, and the level of triiodothyronine decreased. Okay, but what I want you looking at here are these bars, because we've come across them before. Now, these are what we call error bars, and they are showing the variation around the mean of the data that's been expressed on the graph. Okay, so it's important to know, and here you can see your range as it is. So it's important to know what these error bars show, because I have seen them come up in test questions. Okay, so they are error bars. So the variation around the mean of the data. Okay, we move on to controlling appetite, and we're looking now at a hormone called leptin. So leptin is secreted by cells in the adipose tissue and acts on the hypothalamus of the brain to inhibit appetite. Okay, so we've got a diagram there. We're showing where the hypothalamus is, and we're showing the actions of leptin. So let's have a bit of a closer look. Adipose cells, now these are fat storage cells, but we will call them adipose cells. They secrete leptin. Leptin is a protein hormone, just for your interest. The volume of leptin in blood is controlled by food intake and the amount of adipose tissue. Okay, so if you've got more fat cells or more adipose tissue, okay, that has an impact on how much leptin you've got in the blood. Food intake also has an impact. Target cells, they are the part of the hypothalamus that controls appetite. So that's the target for the leptin. So the leptin enters the blood from the adipose cells and it's heading to the hypothalamus. Now, the hypothalamus is controlling the appetite. So if you've got lots of leptin in the blood, then the hypothalamus is going to say, stop. Okay, stop eating. Okay, so if adipose tissue increases, blood leptin levels rise, appetite is suppressed. If you eat, leptin levels increase, appetite is suppressed. And it's that leptin that's in the bloodstream gets to the hypothalamus, binds to receptors, and then the hypothalamus says, let's stop the appetite. Okay, we've got another graph here. Again, I am not too worried about what this graph is actually showing. I've just found some graphs for us to be able to look at. We've got 3 different categories of people. We've got a control group, an obese group, an obese with diabetic group. What can we say? Well, we can say that the obese group had a higher level of leptin within their blood than the obese diabetic and than the control. We've also got error margins there with our error bars, okay, that we can further discuss. But our spread of error is fairly small. Probably our spread of error is the biggest on the obese diabetic. It's just getting used to seeing different types of graphs. That's why I've put lots of graphs in this one, because there are so many graphs to do with hormones. Alrighty, now we're moving on to looking at controlling the circadian rhythms. And a hormone called melatonin is what's used here. So melatonin is secreted by the pineal gland to control our circadian rhythms. So what is a circadian rhythm, first of all? So our circadian rhythm is the natural processes that follow a 24-hour time cycle. And because on planet Earth, that 24 hours is that daily cycle, our bodies have adapted to work to that circadian rhythm. And the pineal gland here is what's going to be secreting our hormone for this one, melatonin. Okay, so primarily controlled by day and night, light and dark. So you can trick your brain into melatonin production. We've got two groups of cells that work on this. The superchiasmatic nuclei, SNC, found in the hypothalamus to control circadian rhythms in humans. These cells control the secretion of melatonin from the pineal gland. So secretion increases in the evening and decreases at dawn. It's removed from the blood by the liver, and high levels of melatonin is what causes sleepiness. Lower levels is what causes you to wake. So it's all about getting that melatonin level right. So here we've got another graph, a nice line graph here. And you see that our graph actually starts at 12, okay? So we're looking at our 24-hour cycle starting at lunchtime, so starting at midday, sorry. And we move through the afternoon, and the melatonin production increases, and then starts decreasing, ready for waking at daytime. Do love a good graph. Alrighty, talking of graphs, controlling the menstrual cycle. So the menstrual cycle is controlled by negative and positive feedback mechanisms involving ovarian and pituitary hormones. We'll have a lot of graphs here. Okay, so basics of the menstrual cycle. The first few days, it depends. A cycle is not always 28 days, but for the basics of learning, we talk about a 28-day cycle. Okay, so the first 5 days or such is the time when menstruation is occurring, so the uterine lining is vacating the body. The next 5 days, you've got the uterus, the lining thickening again. Between day 11 to 18, okay, that's when ovulation's occurring. So you've got your follicles developing the egg, and ovulation then occurs. And then from 19 through to 28, the uterine lining continues to thicken. Hormones are doing things to decide whether fertilization has occurred or not. If not, after approximately 28 days, the menstruation occurs, the cycle starts all over again. Sounds that simple. Not that simple when we start looking at the hormones involved. Okay, I told you I liked some graphs. All right, this isn't as scary as it looks. Let's look at the top first of all. Well, first of all, along the bottom, we're going from 0 days. We've got about mid-cycle, about 14 days when we're going to have ovulation occurring, and then the menstruation occurs again at about that 28 days. So that's along your horizontal axis. Let's go right up the top. First of all, we've got what's happening in the ovaries. Okay, so from 0 days, we've got the follicle growing. Okay, and in the follicle, the egg is developing. About 14 days, we have ovulation occur. Okay, then after ovulation's occurred, we get this formation called the corpus luteum, where the follicle was with the egg in. Okay, and then that diminishes. If we have a look at body temperature, you can see what's happening to the body temperature. At ovulation, there is this slight peak, okay, and then it drops again. Alrighty. Now what's happening with the hormones? We have two hormones that are released from the pituitary gland. That is luteinizing hormone and follicle stimulating hormone. Okay, and you see that they have different peaks. They both peak at about the same time. Similar pattern, do different things. And then we've got hormones that are released from the ovaries. This is estrogen. Okay, there's just so many different spellings of estrogen, but that means estrogen. So we've got what's happening with estrogen, and then what is happening with progesterone. So they're both released from the ovaries. They're actually released from the corpus luteum and the follicles, and a small amount also released from the uterus itself. Now, also, what our image here shows us is what's happening actually to the uterine wall. So we've got the menstruation that's occurring from the start. So the uterine wall gets smaller and smaller because that is lost during menstruation. Okay, and then it starts increasing, because after ovulation, it wants a nice healthy uterus wall for the fertilized egg to hopefully embed into. However, if fertilization doesn't occur, then menstruation occurs and the uterine wall decreases in size. We've got two phases of the menstrual cycle, the follicular phase, which is up until ovulation, and then the luteal phase after. So having a look closer at the follicular stage. This is where follicles are developing in the ovary. Inside those follicles, eggs are developing. Now, only one egg will reach, generally, only one egg reaches maturity and is released. When it's released, that's ovulation. At the same time as those follicles are growing, the endometrium is being rebuilt after menstruation. Okay. Now, the most developed follicle bursts open and the egg is released into the oviduct. Just letting you know that on your course material, you will be calling it the oviduct, not the fallopian tube. Okay, so the egg is released into the oviduct. All the other follicles just break down and those growing eggs just kind of relax back into the ovaries. So that was the follicle phase, which is from day 1 to about day 14. Just remember, in nature, nothing is as simple as that, but that's an approximation. The body temperature is kind of kept pretty constant. What have we got happening with hormones in this stage? So estrogen has started increasing. FSH increases just at ovulation, as does the luteinizing hormone. Progesterone's pretty much constant until just after ovulation. All right, then we move into the luteal phase. So the follicle from which the egg was released turns into this body, what we call the corpus luteum. Now, the corpus luteum is what starts releasing our hormones, estrogen and progesterone. Okay, the endometrium continues to thicken. Now, if fertilization doesn't occur, the corpus luteum and the endometrium then just break down and we start the cycle all over again. And menstruation occurs. All right, so the hormones that we've already spoken about, we've got FSH and LH, so follicle stimulating hormone and luteinizing hormone. They both come from the pituitary gland, and then we've got our ovarian hormones, which is estrogen and progesterone. Just to let you know, we do have one other hormone. So to get the pituitary gland to start doing its thing, we have a hormone called GnRH, which is gonadotropin releasing hormone. Now, this is the hormone that stimulates the pituitary gland to start releasing the follicle stimulating hormone. So we're not actually going to look at that, but I'm just telling you that there is another one, GnRH, and that's gonadotropin releasing hormone. Okay, so that's released from the hypothalamus to the pituitary gland to say, all right, time to start releasing the follicle stimulating hormone. So FSH and LH, follicle stimulating hormone, and luteinizing hormone are both protein hormones. I think we've said that already. And these are both involved in the follicle development and the process of ovulation. So if we look at follicle stimulating hormone, first of all, it's secreted by the pituitary gland. It rises towards the end of the cycle, ready to stimulate new follicle growth. It's not peaking, it doesn't peak or anything, it just starts to rise. Okay. And it also stimulates the secretion of estrogen from the follicle walls. So you'll see as the follicle stimulating hormone increases, as does the estrogen. Again, in this graph, we've got that different spelling of estrogen. That's all good. That means estrogen. Okay, luteinizing hormone. Secreted again from the pituitary gland, peaks at the end of the follicular stage. So we're looking at the blue one here. This stimulates the completion of meiosis in the oocyte, ready to allow the breakdown of the follicle wall for ovulation to occur. Once ovulation's occurred, LH then promotes the development of that corpus luteum. And once that's created, we then get an increase in estrogen and progesterone from the corpus luteum. Okay, then we've got these ovarian hormones. These are produced from the corpus luteum and the follicles, also some from the uterus itself, but only a small amount. So these two are estrogen and progesterone. So estrogen. This is the spelling of estrogen that you use for your IB. There are various spellings, and as I said on this graph that we've got here, it's a different spelling, but sometimes you'll see estrogen with the O as well. This is the spelling we're using. Okay, so estrogen peaks towards the end of the follicular stage. It stimulates the repair and thickening of the endometrium post-menstruation. It stimulates the FSH receptors to encourage more follicles to develop. So we've got that positive feedback now. At high levels, it inhibits FSH secretion, and that's that negative feedback. So it's maintaining a constant for the FSH to ensure that the follicles are developed. It also will then stimulate the secretion of the luteinizing hormone. So estrogen is quite an important one, and it's an interesting one for actually maintaining its levels as it needs. So then progesterone, this increases at the start of the luteal phase. If you have a look, progesterone's been fairly constant all along till here, where it has an increase, then it peaks, then it falls back off or decreases towards the end of the luteal phase. What progesterone does is it promotes the thickening and also promotes the healthiness, maintains that endometrium. It also inhibits FSH and LH secretion. So you see how you've got progesterone and estrogen working against each other as such to give a good balance of the other hormones in a perfect world. Okay, so still controlling reproduction, estrogen and progesterone cause prenatal development of female reproductive organs and then the female secondary sexual characteristics during puberty. So it's saying that estrogen and progesterone are those hormones that really control the female reproductive system. Okay, so up until about day 6, I think it is. Okay, the embryo has no sex as such. It has what we call embryonic gonads. Okay, now is a specific gene found on the Y chromosomes that develops these gonads into testes. Okay, so that gene is the SRY gene. We'll look at that further when we're looking at the male reproductive system, but you need to understand that it's the presence of that gene that develops the testes. So if we've got no SRY gene, then the embryonic gonads develop into ovaries. So no SRY, we're going to get ovaries. Female reproductive organs then develop further using the hormones from the mother's ovaries. So using the progesterone and the estrogen from the mother's ovaries, the female reproductive system develops. Okay, so here we are. A gene on the Y chromosome causes embryonic gonads to develop into testes and secrete testosterone. So that's what we've just looked at, but let's have a look at this a bit further. It's fascinating. So the Y chromosome is present, therefore we've got that SRY gene that we just spoke of, and this codes for the testes determinating factor protein. The TDF, as it's known, then causes the expression of other genes which cause the testes development and then the male reproductive system development. Embryonic gonads therefore develop into testes. Okay, controlling reproduction. So testosterone causes prenatal development of the male genitalia and both sperm production and the development of male secondary sexual characteristics. Now we are going to look at those secondary sexual characteristics shortly of both males and females. But testosterone. So again, I said this is all about graphs. I've been finding any graphs I can. We're looking at testosterone levels by age here. However, at 8 weeks, the embryo is now turning into the fetus, and at this stage we are developing testes. Now, just so that you know, 8 weeks is not on our graph there. Don't worry, I couldn't get a graph that went way back to that stage. So this is 8 weeks in the womb, okay? So we've just developed from the embryo to the fetus, and we're now developing testes. Testes start to secrete testosterone at around 15 weeks. And from there, the rest of the genitalia then develops. At puberty, testosterone secretion, I'll go over this again in a minute, increases, and we get this development of these secondary characteristics. So, hormones and puberty. Now, both males and females have our GnRH, which I spoke about earlier, which comes from the hypothalamus to the pituitary gland. And in the teenage years, these messages start going. Hormones start, messages start then going from the pituitary to the reproductive organs, and developments start to occur. So as you can see, for the male, the voice breaks, growth of muscle tissue, enlargement of the genitalia, and that pubic facial hair starts to grow. For the female, broadening of the hips, menstruation occurs, development of breasts, pubic hair, and other auxiliary hair. So you're looking at like hair under the armpits and things like that. So again, this is just an overview of those changes. So these secondary sexual characteristics, those changes at puberty, all because that GnRH decided to start sending messages to the pituitary gland, allowing that human to enter puberty, which is showing that that human is then at that stage ready to start reproducing as such. Okay, so our applications and skills. First up, we're looking at causes and treatment of type 1 and type 2 diabetes. Okay, so diabetes, a condition where a person has a continuously elevated level of blood glucose. It can cause tissue damage, particularly to proteins. Reduces water absorption in the kidneys, and therefore there is an increased urination and dehydration. So some symptoms of increased sugar levels is there could be glucose in the urine, increased urination, dehydration, increased fatigue, and an increased craving for sugar. Got two different variations on diabetes. Type 1 diabetes is what we call early onset diabetes, and this is where a person has an inability to produce enough insulin. It is an autoimmune disease. The beta cells are destroyed by the body's immune system. It is still very much being researched. And the treatment is testing blood sugar levels regularly, injecting insulin when the levels are too high or likely to become too high, so maybe before meals, and often administered prior to eating. That's the insulin. Much research is still being done in this area. Type 2 diabetes, we call this late onset diabetes. So type 1, that's the kind of diabetes that you will find in children. Type 2, late onset, later in life. And this is an inability to process and respond to insulin due to issues with insulin receptors or blood glucose transporters. Can go unnoticed for many years due to the slow onset. In the past, it's rare in people below 50, but nowadays it's becoming more and more common, and that is because of the associated lifestyle risk factors. Treatment, adjusting diet, eating at regular times, having a low sugar diet, so avoiding high sugar foods, having a low glycemic index, exercising, so they're all factors to reduce that. Your next application, the testing of leptin on patients with clinical obesity and reasons for the failure to control the disease. So lots of studies were done on mice. Injecting leptin did see the obese mice lose weight. However, in humans, it wasn't as successful. There was a trend where weight was lost. However, straight after the leptin vaccinations, when they stopped injecting the leptin, then the weight was put back on very quickly. So it wasn't a successful trial as such. Read more of that on page 332 of your textbook. Application, causes of jet lag and the use of melatonin to alleviate it. Well, what causes jet lag is the fact that you fly between time zones. So you might fly, say you fly from London to Australia. By the time you get to Australia, it might be late at night. But in London, it's early in the morning, and the melatonin and your body clock is still set on what you say London time. Now, what you can do is you can take melatonin tablets or take melatonin to force your body into the new circadian rhythm that you're then in the new country. Okay, and we've got a couple of graphs here. The first one we've already seen, but the second graph is looking at people who tried taking melatonin to see if they overcome jet lag, and according to that graph, we don't know the reliability of the graph because we've got no idea where it come from, but if you look at that graph, it would suggest that taking melatonin does reduce the impact of jet lag. Might be something that I try when I can finally fly again. However, for more information on that, go to page 334 of your textbook. Okay, your next application, the use in IVF of drugs to suspend normal secretion of hormones, followed by the use of artificial doses of hormones to induce superovulation and establish pregnancy. IVF stands for in vitro fertilization. So basically what it means is eggs are withdrawn from the female, sperm is taken from the male. They are mixed in vitro and then observed to see if fertilization has occurred, and whether an embryo develops, then that embryo is placed back into the uterus. Let's have a look at what goes on in IVF. So as part of the IVF procedure, a woman's eggs are harvested from her ovaries. However, you need to get the ovary to hyperstimulate first of all. So during the first 2 weeks, the female is given a drug, usually a nasal spray. It can also be an injection, okay, and the injection goes into the stomach. And this suspends her natural hormones, so FSH and LH, and suspends the full menstrual cycle. Sometimes it's also done with a contraceptive pill. Okay, so what this does is this enables doctors to be able to control the timing of egg collection, and this is timed to the hour, quite literally. Okay, for the next 12 days or so, she has to inject with a range of hormones. They include FSH, so you want to stimulate the follicles. They want to hyperstimulate. Okay, so they want to be able to withdraw as many eggs as possible. So this results in many follicles developing on both ovaries. Okay, that's just actually an interesting point there, because when we look at the menstrual cycle, one ovary releases an egg each month. Okay, whereas here both ovaries are developing follicles. The production of many eggs, more than normal, because usually you'd only have one, so we call this superovulation. So then a trigger hormone is injected, and shortly after that you've got to get into hospital to have the eggs harvested surgically, which involves being knocked out, and yeah, they go in through the vagina to extract the eggs. At the same time as the eggs are being surgically harvested, the sperm has to be collected from the male, who needs to ejaculate into a container. Once you've got the eggs and the sperm, as I said, they're placed in vitro together to hopefully allow fertilization to occur. Microscopic observations are made. If the embryos develop, between 1 to 3 embryos are replaced into the woman's uterus. Okay, and any other healthy embryos can be frozen for later use. This, you may see this image sometimes when you're talking IVF, and that is called ICS. Now, some couples, infertility is not actually about the egg as such. It may be that there's an issue with the sperm, in which case using IVF may not work, because by just placing the egg into a solution with the sperm, if the sperm don't swim, they've got inactive towels or something like that, then fertilization won't occur. So what you can do is they can find one healthy sperm and actually inject it into an egg, and that's the image you're seeing here, and this is called intracytoplasmic sperm injection. Okay, so the whole IVF process occurs to obtain as many eggs as possible, but then the sperm may be injected into the egg. Okay, our next application, William Harvey's investigation of sexual reproduction into deer. Now, as we said earlier, William Harvey was fascinated with biology, and he was investigating the blood circulation. He was also investigating reproduction in deer. Now, he believed Aristotle's, so he was brought up believing Aristotle's claims that the male seed turned into an egg and then was implanted into the female, but had to mix with her menses, so basically with her menstrual bleeding. Okay, but he realized that this potentially wasn't true. Now, he tried to do further investigations around this, looking at deer, but as we said, because the microscope hadn't been developed at that time, his discoveries were halted as such. More information on page 339 of your textbook. And finally, your last skill of SL biology is to be able to annotate diagrams of the male and female reproductive systems to show their names and functions of all the parts. So male reproductive system here, female reproductive system here, and if you go to page 336 of your textbook, there's a brilliant table telling you what each of the parts does. Take it easy, and thank you for watching SL Biology with me.